Dear students, in EV visible spectroscopy, excitations it is the important point. So we have to see how these excitations in EV visible spectroscopy will happen. So this EV visible spectroscopy measures absorption of the ultraviolet, that is between 185 to the 400 nanometer and visible 400 to the 700 nanometer light, which causes electronic transitions of the valence electrons from the ground state orbitals, bonding or the non-bonding, to the higher energy anti-bonding orbitals. The key transitions includes pi to pi star conjugated systems, n to pi star in carbonyls, identifying chromophores and quantifying concentrations via Beer's law. There are some important electronic transitions are present in between EV visible spectroscopy, that is pi to pi transitions, involves excitations of the electrons from a bonding pi orbital to an antibonding pi star orbital. These are common in unsaturated conjugated system. Examples are carbon-carbon double bond or the aromatic rings, and typically occur in the UV region. Then second transition is n to pi star transitions, involves non-bonding electrons, that is lone pair, on oxygen, nitrogen and the sulfur, exciting to an antibonding pi star orbital. These generally require lower energy, longer wavelength than pi to pi star transitions. Then sigma to sigma star, it is also the another important transitions, occur in saturated compounds, that is presence of carbon-carbon single bond or the carbon-nitrogen single bonds, requiring high energy UV light, often below 180 nanometer, which is less common in standard UV visible spectroscopy. Then important transition is n to sigma star transitions, occur in saturated compounds containing heteroatoms with lone pairs. Then charge transfer transitions, common in transition metal complexes, where the electrons move between the ligand and the metal orbitals. Then there are some principles of the excitations, that is chromophores, specific functional groups responsible for the absorption, such as carbon-carbon double bond, carbon-oxygen double bond, and the nitro groups, HOMO-LUMO gap. The energy absorbed corresponds to the difference between the highest occupied molecular orbital HOMO and the lowest unoccupied molecular orbital LUMO. The conjugation effect increases the HOMO-LUMO energy gap, decreases causing the absorption to the shift to the longer wavelength, the atrochromic shifts.